welcome you back to our table and celebrate with you our 300-year-old traditions. And we know that you will create new ones along the way.
Good morning, New Orleans. We love you, New Orleans.
Just know that we're thinking of you here in the Crescent City, and we can't wait to see you soon.
Love New Orleans. When people come, they never leave because we're swinging that way. The sun shines so bright. The breeze is so nice.
We propose a multi-perspective simultaneous embedding (MPSE) algorithm for visualizing high-dimensional data based on multiple pairwise distances between the data points. MPSE computes positions for the points in 3D and provides different views into the data by means of 2D projections that preserve each of the given distance matrices. MPSE works on abstract data as well as graphs.
Exploring the emotions of students in classroom videos can help both teachers and parents know about students' learning status and further help teachers improve teaching. However, it is a non-trivial task to analyze the emotion evolution of a group of people from classroom videos due to three major challenges. We propose a visualization system which integrates the model uncertainty and supports both collective and individual emotion analysis.
We present columnar data augmentation through visual analytics. Kava lets users augment their data with additional attributes found on knowledge graphs. To construct a new attribute, each row of a dataset is mapped to a node on a knowledge graph. Each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node.
It is common for users to struggle to understand how to effectively use TS&E. No idea how to select hyperparameters, assess the quality of the results, investigate the existence of shapes and other patterns. TVS&E covers all these tasks. We provide diverse projections to choose from, global and local quality assessment, investigations of shapes and patterns, and more.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Many feminist strategies pay little attention to the preservation of significant contextual structures. In its paper, we propose a context-aware graph sampling method in a vectorized space to preserve not only contextual structures but also significant topological features. Welcome to pay attention to our paper. Its ID is 1259.
traditional clustering tools do not include users in the analysis loop. We present PK clustering, a new approach for interactive clustering using VIS. First, users specify their prior knowledge. Several algorithms are run and match with the prior knowledge. Users then build a consolidated clustering iteratively with suggestions based on consensus, the graph, and their knowledge of the data. The result is a consolidated clustering.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought. Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend.
Hello, everyone. This is Evanthia Dimara, chairing this session, Emotion and Cognition. And I'm really happy to chair this session because here in VIS, we have a very heated discussion right now on how the visualization domain can move beyond the study of perceptual accuracy in the way of Cleveland and McGill type of works. So I think all the works presented in this session are somehow paving this path of what else we can test to assess the value of visualizations. So we are starting with our first presenter for today, Alireza Karduni, who will tell us, Alireza is from UNC Charlotte University, and Alireza will tell us how we could possibly study belief updating about correlations through visualizations with uncertainty.
Hi, my name is Alireza Karduni. Hope you're all doing great and safe, obviously. Today I will be talking about a work called A Bayesian Cognition Approach for Belief Updating of Correlation Judgments Through Uncertainty Visualizations. This work was done with my dear co-authors, Markant, Wesslen, and Wenwen Dou, and we are all from UNC Charlotte. What do you believe is the correlation between labor union participation and corporate profits of different companies? Now let's look at a scatter plot showing a sample data about these two variables that we just thought of. Does this scatter plot confirm what you originally thought of, or is it very different from what you believed? How much did you update your belief after seeing the scatter plot? What if, instead of this chart, we had shown you a dataset with more uncertainty, with only 10 samples? Would that make you more or less uncertain? In this research, we explore such questions. We study belief updating about correlations through visualizations with uncertainty. We conduct 3 studies. First, we introduce an elicitation method called line plus cone to quickly elicit users' belief and uncertainty about correlations. In the second study, we investigate how users update their beliefs about bivariate relationships in light of different visualizations with and without uncertainty depictions. In the third study, we investigate how users update their beliefs when data visualizations are congruent or incongruent to what they originally thought of and have high or low amounts of uncertainty. So first, let's talk about this elicitation method that we created. We call it line plus cone because first users use the mouse to hover and select the line that best represents their beliefs about the correlation between 2 variables. After clicking, users would again hover and select a range that would represent other plausible alternatives to the correlation of these variables. So in study 1, we try to ask the question of whether line plus cone can capture users' beliefs and uncertainties about correlations. We compare it to another method called Markov chain Monte Carlo with people, or MCMCP, which is a method for estimating subjective belief distributions based on a series of force choices. So in study 1, users go through 5 variable curves, once with the line plus cone method and once through the MCMCP visualization. We found that instead of collecting a large sample from users' choices through the MCMCP method, which would be cumbersome, we could use our 2-stage line plus cone method to arrive to belief and uncertainty values that are significantly correlated with the values we arrive at using MCMCP. Study 2, we asked whether different visualization types impact the extent to which users update their beliefs about correlations. And our hypothesis, inspired by studies on confirmation bias, is that users would show less belief change when visualizations include depictions of uncertainty about the true population correlation. In study 2, each user goes through 10 variable sets, 5 variables for 2 rounds, and elicit their beliefs before and after seeing the data visualization about each variable set. In round 1, the user would view 5 variable sets through only scatter plots. And in round 2, users are randomly assigned to either of 3 different visualization groups: line, cone, and hops. The scatter plot condition and the line condition do not include any explicit visualizations of uncertainty, and the cone and hops conditions represent uncertainty differently. We used linear mixed effect model to model the differences between the conditions and test our hypothesis. The dependent variables in our models are absolute belief difference, that is the difference between the 2 means that users elicit. Uncertainty difference, that is the difference between the 2 uncertainty ranges. And distance to sample correlation, that is the distance between users' posterior belief and the sample correlation. The independent variables, or fixed effects, are visualization types: scatter, line, cone, or hops, and the absolute correlation of the generated data. The results showed that scatter plot visualizations, augmented with representations of the sample correlations, such as line, cone, and hops conditions, led to greater accuracy in posterior beliefs compared to the scatter condition. In addition, the cone visualization with a cone of plausible alternatives representing uncertainty in the correlation led to greater reductions in self-reported uncertainty. However, we did not see a difference between users' belief change between these conditions. Using Bayesian cognitive model, we try to explain our users' behaviors in this study by asking whether having elicited prior beliefs about each set of variables can participants' posterior beliefs that come after the visualizations be predicted by a normative Bayesian model. We created 3 models to do this. First one is prior only, and that would be if users would completely stick to their priors and not update their belief at all. We call the second model Bayesian-informed, and that is if users update their beliefs in a Bayesian manner by incorporating their elicited priors rationally. And the third model is one where users would not incorporate their priors at all, and we use the uniform distribution as a prior for this model, and we call that Bayesian uniform. We compared each of these models through two metrics of KL divergence and mean absolute error of the difference between each model and users' elicited posteriors. So this chart, interestingly, shows the performance of each model within each condition. As we can see, users' posteriors were best fit by a Bayesian model with a uniform prior, suggesting that the sample correlation and the data visualization had a stronger influence on users' belief updating than their individual priors. So in study 2, compared to the scatter plots, representations of population correlation led to greater accuracy in posterior beliefs. Less uncertainty in the data, meaning stronger correlations, led to lower posterior uncertainty. Uncertainty representations, such as cone visualization, led to lower posterior uncertainty compared to other conditions. And posteriors were best fit by a Bayesian uniform model. Data had stronger influence than expected from a rational model, especially when the data was incongruent to users' priors. So the results of study 2 gives us some motivations for study 3. First, most data sets were congruent to users' prior beliefs. And we did not control for the amount of uncertainty shown to users for different sample correlations. All scatter plots had 100 points. So in study 3, we want to ask what happens when correlations shown are incongruent to users' belief? And what happens when data sets shown have high or low sample uncertainty? Our hypothesis is that viewers of uncertainty representations would exhibit smaller changes in beliefs when correlation visualizations are incongruent with users' prior beliefs, and when the dataset has a smaller sample size. In study 3, we had 16 variable pairs that were predetermined through a small pilot study, and each were assigned to be either congruent or incongruent, and either have 10 samples or 100 samples. In the congruent condition, users would see datasets with correlations that have the same sign and are on average 0.25 points away from users' priors. And in the low uncertainty condition, users would see datasets with 100 samples. In the high uncertainty condition, users would see dataset with 10 samples. And in the incongruent condition, users would see generated dataset with correlations that have a different sign and were on average 1 point away from users' prior. In this study we had similar dependent variables, absolute belief difference, uncertainty difference, and distance to the true correlation. And then the independent variables were visualization types, line, cone, or hops, and then pre-belief distance and sample uncertainty. Pre-belief distance is the distance from users' prior elicited mean to the correlation of the sample dataset. And sample uncertainty is the size of the confidence interval that was shown to the users. The results show that within the cone and hops conditions, and for variables showing incongruent correlations, users were more likely to have smaller belief change, and that is evidence in support of our main hypothesis in this study. We also found that similar to the results of study 2, a cone condition amounted to a more likely reduction in uncertainty for users, and that for both the cone and hops conditions, for dataset with larger uncertainties, we see an increase in users' uncertainty. We used the same 3 prior-only Bayesian-informed and Bayesian-uniform models to study users' belief change and tendencies. The results, again, showed that in most conditions, the Bayesian-uniform model was best fit to users' elicited posteriors, although with one really interesting exception. In the incongruent condition, and when users were assigned to the cone condition, the performance of the Bayesian-informed model was comparable to that of the Bayesian-uniform model, meaning that users in that condition had a more rational incorporation of their priors in updating their beliefs. So, how did the Bayesian uniform model best explain users' posteriors? One explanation for this could be that people might have a different interpretation of the cone representation, which is used to elicit their uncertainty. Even though in study 1, we found support for the claim that this method captures participants' uncertainty, there may nevertheless be a mismatch between the elicited distribution and participants' subjective beliefs, such that people are more uncertain than indicated by their elicited priors. So, why did the cone condition amount to smaller belief updates for incongruent dataset? Was that due to confirmation bias? The results of our Bayesian cognitive model offers an alternative interpretation for this. Rather than representing an irrational failure to modify beliefs due to confirmation bias, the cone condition may be the most effective for striking the appropriate balance between new data and prior beliefs. And in conclusion, in this study, we showed that eliciting belief and uncertainty helps us better understand how users are affected by data visualizations. We also showed the importance of uncertain visualizations and how that affects users' belief update facing different types of visualization. And then we showcased how we can use Bayesian cognitive models for understanding individual and group tendencies when using visualizations. And with that, I would like to thank you all for listening to my presentation, and would be happy to take any questions.
So thank you very much, Alireza, for this very exciting presentation. So now we can proceed to our Q&A. I can see one question coming from Alex Ale. You see updating behavior that wasn't predicted by any of your three models, prior only, Bayesian inform, and Bayesian uniform?
That's a really good question. We didn't really specifically look at those. We should have, but didn't look at individual like outliers or things that might have those interesting cases to interpret. But that's something that we probably should look at.
Very nice. So we still have one time for one more question. Anybody not being too shy here? Nobody. So it's my time for a question. So, you know what I was wondering, from your experience running all those studies, are people really able to express their prior beliefs? I mean, is there a chance that we might prime them over not admitting that they don't know how, that there is, whether there is a correlation, or there is certainty of a lack of correlation in the data? I mean, is it really easy to capture those sort of prior beliefs?
So that's also a really good question. This is one of the biggest takeaways of our paper. One, so we did study one to compare it to a more established method to be able to elicit both people's beliefs and uncertainties about phenomena. Now, the idea of including the cone in the visualization is to help us to kind of differentiate people who are more sure or more confident and more inconfident. However, the fact that we had this phenomenon where the Bayesian uniform model was predicting was the best fit kind of had something to say about that maybe, even though people are using this cone method to elicit, to show us their uncertainties to some extent, maybe that still is not capturing their actual, how invested they are to those prior beliefs. We might believe, as in terms of numbers, if the range is really small, we might believe this guy will not change their belief at all. But it looks like even in smaller uncertainty ranges or larger uncertainty ranges, that behavior is still, the data has a lot of effect on users. And one of the explanations could be that the uncertainty range is not still capturing the whole story. However, because we saw that when users were exposed to uncertainty representations in incongruent conditions, people actually did update less. So we actually saw an effect on that of uncertainty with people's uncertainty. We believe that to some extent it's capturing users, both kind of belief in correlation and how sure or uncertain they are about the correlation.
Very interesting. Thank you, Alireza, for this very illuminating answer. So now we can move on to our next speaker, Yea-Seul Kim from the University of Wisconsin-Madison. So Yea-Seul will present to us two interventions of how we can actually improve such belief updating. So Yea-Seul, the stage is yours.
Hi, my name is Yea-Seul. I am an assistant professor at the University of Wisconsin-Madison. This work has been done while I was in the University of Washington, working with Jessica Hullman, Paula Kayongo, and Madeleine Grunde-McLaughlin. So visualizations help people to form beliefs about the world around them. However, we know from research that people often struggle to properly account for how informative or conversely uncertain data is when making judgment and decision from data. For example, there is data flying around about how prevalent COVID is among students as college reopen. Imagine you foresee on estimates from a large public university in your state saying that a couple of weeks into the semester, 3% of 300 total students tested had COVID. And then you encounter a new result from 1,000 students from a second demographically similar public school in your state. Based on the testing of 1,000 students, it reports that the infection rate is likely to be 12% with a high confidence. It's between 10% and 14%. Now that you've experienced both estimates, what would your best guess of average prevalence be at large public school in your state? So what you believe, including how certain you are, represents your posterior beliefs. So this beliefs updating process happens all the time implicitly when people interact with visualization. However, visualization researchers rarely study this in visualization evaluation. How can we evaluate a set of posterior beliefs? So one way to evaluate is to compare the posterior with some type of rational standard. The law of Bayesian beliefs updating prescribes an optimal way for combining prior and new information. Assuming that you have no reason to distrust the new evidence, you should update your belief proportional to the amount of information that new results provide over what you already believed. Based on Bayes' rule, the new belief should be around 11%, with a high confidence interval between 9 and 13%. This Bayesian standard helps us diagnose how user poorly understanding of uncertainty and whether people overweighted or underweighted the new data. In our prior work, we used a Bayesian approach to evaluate inference from visualization and found that at an individual level, most people updated belief deviates from normative Bayesian inference, slightly overweighting for small samples and grossly underweighting large sample. Our results aligns with more general findings from research on bias in economics and psychology. If many people are biased, it makes sense to ask, how could we intervene to improve their belief updating? A natural solution that we explore in our prior work is to improve how uncertainty is visualized in the data so that they can recognize how much information they're gaining from a new data sample. However, while animated uncertainty visualization clearly helped, we still observe a pretty big difference in some cases in how a perfect Bayesian would weight evidence and how the average person does. So in this work, we designed two techniques to further close the gap. In designing techniques, we want to make the amount of information in the new data relative to their belief meaningful. So we designed the uncertainty analogy technique where we express the uncertainty of the observed data using how uncertain their prior is. So in this case, the observed data contains 3 times more information. So we formulate the analogy saying the data has 3 times more information than your prior, so that the user can contextualize how uncertain data is relative to their own beliefs uncertainty. So we also consider showing the normative posterior beliefs directly to the user. We call this technique posterior visualization. So in our work, we tested the effect of these techniques in improving people's belief updating. So again, the uncertainty analogy shows the observed data alongside an analogy statement that re-express how much uncertain the observed data has using the uncertainty in their prior. In this example we used in our study, it says your prior has 2 times more information than the data, and the study data is 2 times more uncertain than your prior. The multiplier is changed based on their prior. Posterior visualization presents the posterior beliefs predicted by Bayesian inference given the user's prior beliefs. For example, in addition to the observed data, we can show the beliefs that the user should have if they have no reason to distrust the data, which is the normative posterior beliefs. In a study with 4,800 participants, we varied a few factors to test their impact. So since not trusting a data set is another possible reason for the deviation between one's posterior beliefs and the normative posteriors, to choose the data set that varying in controversiality of the topic, we ran an Amazon Mechanical Turk study to find these data sets as representative of not trusted and trusted data set. The dementia dataset was identified as the least controversial dataset that described the percentage of assisted living center residents in US has Alzheimer or other form of dementia. Abortion dataset was identified as the most controversial one that describes the percentage of people in the US think that third trimester abortion should be always illegal regardless of the circumstance. The sample size is one of the factors that we observed in our prior work that influence belief updating behavior, so we vary that in this experiment as well. So our study is starting by eliciting participants' prior beliefs. And then participants examine the data representation. We have Bayesian-Assisted technique condition, uncertainty analogy, and the posterior visualization. And to test those effects against the best suggestion that visualization research currently makes, we add uncertainty visualization condition, where participants would see only the observed data with its uncertainty, which serve as our baseline condition. And another very common visualization we often encounter is just a point estimate, where uncertainty is only mentioned in the form of reporting the sample size of a data set in text. The participants in this condition see only the point estimates of the observed data without seeing any uncertainty representation. After examining the data presentation, we elicit their posterior beliefs again. To analyze the study data, we fit the participants' elicited belief to a distribution. And then we calculate each participant's normative posterior by merging their prior and the observed data using Bayes' rule. And then we're going to compare the normative posterior that indicates the participants should believe if they are a perfect Bayesian with their actual posterior distribution. So we would like to see if participants in the Bayesian-Assisted technique condition have smaller difference compared to participants in non-Bayesian-Assisted technique condition. We analyze the experimental results in 2 ways. Using the qualitative scheme to classify patterns of bias we observe and using a model. To get a qualitative understanding of how people's belief updating can be biased, we characterize different ways one can update based on where their posterior is located. Imagine a user's prior and the data are located like below. The normative posterior will be located in between the two. So we classify the participants as near normative when their posterior is located relatively close to the normative. If the participant's posterior is located in between their prior and the normative posterior, we classify this case overweight prior because it's the result of weighting their prior more than they should. We classify the participants as overweight data when their posterior is located between normative posterior and the data. So some participants' posterior located further than the data, and we call this case overshoot. Here we see a histogram where rows represent different data sets and columns represent how the observed data was shown. These first results indicate how far off the location of people's belief or where they are centered were from the location of the normative Bayesian posterior beliefs. We observed that the most frequent category of location update was to roughly Bayesian. As you can see, the majority of participants fall in the near normative category. However, we observed that participants who are in a point estimate condition, they are least likely to fall in the near normative category, whereas participants in the posterior visualization condition were the most likely to fall into near normative category. So we took a similar approach to classify participants' updates in terms of the variance of their posterior. So when the variance of the participants' posterior were similar to the variance of normative, we classified them as close to normative. We also classify when those were smaller than the normative and the larger than the normative. So when we look at the variance of dating, there were clear systematic bias regardless of condition, which generally participants were remaining more uncertain about the parameter value than they should have compared to the Bayesian standard. Perhaps as a result of the strength of the systematic bias, we don't see a clear advantage of Bayesian assistance. Also, we observed that participants who saw the small datasets were overconfident more frequently than those who saw the large datasets. Besides this categorical analysis, we present the result of a pre-registered regression model. So this model used another way of looking at the difference between normative posterior and the participant's actual posterior, which is to calculate the KL divergence between the two distributions. So KLD is a single information theoretic measure that quantifies the difference between two probability distributions. It captures both location and variance deviation from the normative Bayesian updating. So as you can see here, if two distributions are close together or more similar in variance, KLD has a lower value. Whereas if they're further apart or their variance differ more, it has a higher value. So see our paper for many observations we can make from the full model results. Here I will present highlights from just one of the submodel, which we use to analyze bias in participants' update. And as I mentioned, the uncertainty visualization is our baseline. So every estimate is compared against the uncertainty visualization condition. In small sample dementia dataset, Bayesian-assisted techniques reliably decrease bias, meaning that techniques helped people form beliefs that were more similar to the normative posterior. And our qualitative results suggest that this result is driven by better location updating. In large sample dementia, only the posterior visualization reliably reduced bias, again probably because of better location updating, but not the analogy condition. And in small sample abortion dataset, similar to dementia small dataset, both technique reliably reduce bias in KLD. However, in large sample abortion dataset, neither technique worked. This suggests that when faced with a large dataset on a topic they don't trust a news source on, they may simply reject the data out of fear that it's propaganda. An important thing to note about our results is that they show that Bayesian assistant can be helpful for small and even some large datasets, even over to the benefit of uncertainty visualization. So while I didn't cover it in this talk, the effect size of Bayesian assistant were slightly larger when comparing to a point estimate, which is the most common way people tend to look at the data. We think that's exciting because it suggests that taking into account of people's subjectively meaningful prior beliefs in visualization interaction can lead to affect types of automatically generated assistance. And we think these results could be useful if applied in a visual analytics systems where user may have some prior and then they can articulate, or prior might be learnable from past data of the same type. And they could also be useful in more casual setting to help people better recognize how much information a new data set brings. The results we saw appear to be driven by people better recognizing what the most likely estimate should be. So people still struggle to update the variance of their beliefs properly. We think there might be interesting work to do to better understanding why this sort of conservatism or uncertainty is so common in human belief updating from data. We asked one other question in our work, which I'll briefly highlight now. The question is, what is the effect of prior elicitation itself? Could that alone be useful? So in our experiments, we also varied whether prior were elicited or not for the uncertainty condition and the point estimate condition. So we can't look at the individual bias between elicitation condition and non-elicitation condition since we don't have prior distribution data from non-elicitation condition. But we can do an aggregate level analysis informed by those used in mathematical psychology, where we assume that the aggregate prior from all participants who gave us belief will be the same across another large set of people drawn from the same population. We found that across the board, elicitation conditions yield lower KLDs, suggesting that prior elicitation alone may improve updating. You can find more detail in our paper. All right, thank you.
Thank you very much, Yea-Seul, for this really thought-provoking work. So there are a lot of questions on Discord, so unfortunately we only have time for one of them, and I hope you can join later to answer more. So Michael Corel is asking, given how overloaded is the world information is in common usage, I wonder if you tried different textual analogies for the data's importance compared to their prime.
Yeah, in this study setting, we didn't particularly explore multiple ways of expressing the analogy, but we, during formulating our study hypothesis and study stimuli, we've been talking a lot, how should we present, how should we formulate the textual analogy? Our priority was understood by lay people, so that they at least get the understanding behind like what we were trying to do. But it's a great question. Maybe there are some other effects. Some might be more effective, some might be less effective, or some might guide into some different direction and so on. So that's an interesting future work.
Very nice. Thank you, Yea-Seul. And this is for now our end of the Q&A session. Now we are moving forward to our third talk for today from Christian Heine, where he will tell us how can we reduce the cost of such evaluations by using predictive models such as Bayesian networks. Christian, the stage is yours.
We all know from experience that designing functional visualization systems is difficult. To increase the chance of success, we therefore use heuristics and guidelines during design. These are distilled from designers' long-term experience, but we can also assess the quality of a design using heuristic evaluation, or alternatively, compute and compare metrics of applications of this design. Unfortunately, these strategies aren't necessarily reliable or valid. Therefore, we often have to resort to empirical studies to test whether a visualization system is indeed effective. But these studies are time and labor intensive. So the question I'm asking is, can we reduce the cost of evaluation by automating it? To automatically evaluate a visualization system, we need general theories and models that allow to predict the effects of visualization use on its users. Currently, we do not have such models. In this talk, I will discuss what it will take to research them. Some models have been proposed for parts of visualization processes. However, these often model only data flows and transformations inside a computer, while the human is just a black box with unspecified behavior. There are also many conceptual models. These may point out so-called leverage points, but make no predictions about how operating on them exactly affects the properties of a design. Recently, some attempts were made to model perceptual processes and used to fine-tune visual design. But these are usually technique-specific and do not address interaction design or how information is processed further by the human. Largely unknown to the field of visualization are models of higher level human cognition and psychology, even though they are used for evaluation in the field of human-computer interaction. But these models consider no or simplistic visualization settings, for instance, reading off and comparing single values from commodity charts. Can we bring all of these different approaches together? What does it take to build a general modeling approach suitable for describing the effects of visualization system use on its users? Well, the first step in any modeling is selecting a modeling paradigm guided by the properties of what is to be modeled. So what are the general properties of visualization processes? First, visualization involves at least a human and a computer. Therefore, models need to be able to describe both human and computer behavior. This was already recognized in the NSF report on visualization in scientific computing. Second, interaction is deemed a fundamental ingredient to visualization. Humans aren't passive consumers of the images computers produce, but converse with an information space through the computer. Therefore, models should allow to describe the dynamic mutual influences that underlie human-computer interaction. Third, the purpose of this conversation is to build knowledge, inform decisions, solve problems, and so on. It is generally recognized that visualization is not about pretty pictures, it is about insight. Hence, models should capture users' cognitive state at least in terms of knowledge change. If cognition is what mediates between perception and action, then models capable of explaining how humans will interact with the computer need to model some of these cognitive processes as well. Fourth, models should be able to describe the processes generating the data. Data are not always faithful mirrors of the facts. They may be afflicted by systematic or random errors, or even be fabricated. Knowledge generated through visualization should be about the facts, or more generally, the properties of the data generating process. In some instances, for example computational steering, users will even want to influence the data generating process. So it is beneficial if models could capture this as well. Fifth, models should describe visualization processes as time-dependent. This follows directly from the dynamical nature of interaction. It also captures that data may be streaming or its generation be influenced by the user dynamically. And of course, performing tasks with visualization systems takes time. 6. Models should allow for the description of stochastic effects. Data arising from measurement is usually subject to errors, which can be modeled stochastically. Visualization algorithms can be probabilistic. Our whole neural architecture is probabilistic. But most importantly, stochastic features allow for partial models where all unmodeled factors are simply treated as noise. 7. Models should be computational or mathematical and allowed to be simulated. This is simply because models will reach a complexity that makes it impossible for human designers to use them unaided when making predictions about the effects of visualization system use on its users. In summary, the modeling paradigm we seek needs to be able to describe time-dependent, stochastic, mutually influencing processes within computers and users. These processes relate users' cognitive state to properties of the data-generating process. We have a list of requirements. We need a set of modeling paradigms to apply them on. Note that actual models of visualization processes will differ based on the visualization techniques used, but visual information processing by the human will be mostly the same or subject to few parameters for individual differences. When selecting a modeling paradigm, it is thus useful to focus on models of human information processing and discuss their ability to be extended to include a visualization system. One might also argue that human-centered design matches well with human-centered modeling. Models of human information processing are studied in the field of mathematical and computational psychology. Without going into too much detail here, there are 5 large modeling paradigms. Cognitive architectures usually use rule-based programming languages and are tuned for describing problem solving. Logic-based declarative systems focus on the knowledge an agent needs to solve a certain task. Connectionist models use neural networks and perform well for recognition tasks. Dynamical models use systems of partial differential equations to describe, for example, smooth body movement. Bayesian models of cognition are motivated from the need to describe human reasoning under uncertainty. But there are also hybrids of these 5 approaches. Most of these modeling paradigms can be ruled out, because either they do not allow to describe time-dependent stochastic processes, or describe the computer part would be cumbersome. Within mathematical psychology, proponents of Bayesian methods have realized their potential to model not only reasoning under uncertainty, but any process that can be described with probability distributions over many variables. Bayesian networks, a type of probabilistic graphical model, can be viewed as a data structure to efficiently store and operate on joint probability distributions of many variables. Conceptually, Bayesian networks store a joint probability distribution as the product of conditional probability distributions. Exploiting conditional independence between random variables gives compact representations. Graphical representations show the dependencies of variables as a directed acyclic graph. Dynamic Bayesian networks interpret each node in a graphical representation as a temporal sequence of random variables. Their conditional probability distributions depend on the variables from the previous time step only. Dynamic Bayesian networks thus describe Markov chains, and one can show that all computational processes are special cases of Markov chains. Therefore, dynamic Bayesian networks can model both processes within computer and human. The latter have been modeled with great success using cognitive architectures which are computational in nature but not stochastic. As a further benefit, the parameters of Bayesian networks can be learned from observational data. Note, however, that adapting dynamic Bayesian networks does not entail modeling human reasoning as following Bayes' law, or that knowledge is modeled via degrees of belief, which is assumed by proponents of Bayesian models of cognition. This figure shows the potential structure of a dynamic Bayesian network for describing visualization processes. It was compiled from multiple prior conceptual models of visualization systems and human cognition. Intentionally, the computer part of the model is kept simple to emphasize the interaction between human processes. Note that not all variables of the model, for example goals in working memory, are empirically observable. Bayesian networks allow in principle to infer their values from the values of observable variables, in the case of this model, eye fixation and hand position. However, this is not a full model since only the structure but not the conditional probability distributions are given. I therefore suggest that we establish a research program to study these probability distributions. This program has the benefit of unifying much of the empirical research going on in our field, but will take decades to complete. I suggest we start with minimum working prototypes for single visualization techniques, which we then unify and extend. Researching these models will have many applications. For one, we would be able to observe the effects of visualization system use on its users in a simulation. In educational settings, this can be used to give students of visualization a feeling for the many processes going on in the user's mind. Simulations can not only show whether a visualization system produces the intended effects, but also whether there are undesired side effects. They can thus help to specify the conditions under which a visualization system is deemed effective. Studying the effects in the simulator can serve as a proxy to evaluation. Playing through what-if scenarios and studying the influence of parameters within the computer part of the model can indicate directions for improving a design. Finally, if such a model were integrated into the visualization system itself, it could reason about users' progress and support them in their tasks. Note, however, that it will be unlikely to actually predict the behavior of individuals due to individual differences, but we might have success for groups for which we can determine the probability distribution over these differences. To conclude, we should make a concerted effort to study models for explaining and predicting how humans interact with visualization systems and how that affects their cognitive state, such as their knowledge. Dynamic Bayesian networks have many favorable properties that make them good candidate models. Simulations of these models will be useful tools for the design and evaluation of visualization systems, but much more research is needed in this area.
Well, thank you very much, Christian. That was a really nice point that you made about predictive modeling. Unfortunately, we only have time for one question. You can respond to the rest of them on the chat. So from Danielle, she's asking, how do the core properties you presented differ related to those central to cognitive architectures or their implementations in the HAI or UX context?
Yeah, that's a good question. I mean, first of all, cognitive models are a wide field. There are many different types of cognitive models, and not all of them actually support every of these 7 requirements which I presented. For instance, the popular cognitive architecture ACT-R is not really suited for describing probabilistic features. You can do it, but it's quite cumbersome. Or for instance, or the logic and declarative based modeling, they are not really suitable for describing time dependencies or actually how long something will take. Yeah, it's really difficult to pick the best one, and I'm also actually not very happy with the result of Bayesian models, because they're quite well, models in them will be very will have many parameters and will be very large. I really was hoping for something like ACT-R to be the winner there, but well, I think the disadvantages just outweigh there. Yeah. But anyway, I encourage everyone to look at the paper, because, you know, a 12-minute talk can't really give the justice to every little argument that I have in this paper. So, but thank you for the question.
Excellent. So I think you're going to have a great audience down there to discuss all those implications of modeling. And this for now is our ending of the Q&A session.
Thank you.
Now we will have our 4th presentation for today from Chen and University of Helsinki. We have a lot of discussions about information and insights and knowledge. So Chen will tell us how can we capture the knowledge or the insights by analyzing user interaction. Chen, the stage is yours.
Hello everyone, my name is Chen from the University of Helsinki. Now I'm going to talk about our paper titled Characterizing the Quality of Insight by Interactions, a Case Study. As claimed by many researchers, the main purpose of visualization is insight, not the pictures. Understanding user insight generation process is very important in designing effective visualizations. For instance, Ye and others discovered 4 major processes that support insight generation in visualization: based on literature review. They are providing an overview of the data, allowing users to adjust the perspective on the data, supporting pattern detection, and matching users' mental models. As insight results from user interactions with the data, previous research also explored the relations between interaction and insight. Guo and others categorized user insight by facts, hypotheses, and generalizations. And they discovered that filtering type of actions inhibits the number of facts generated, whereas exploration actions promote it. This work proposed to use transition graphs to link visual exploration and user insight. The green nodes in the left-hand figure indicate visual exploration and the blue nodes indicate insight generation. The red links represent the transition probability increased after the user switching from a small to large display. The detailed variations are shown on the right side. For instance, the outlined cell indicates with the larger display, users tend to make a series of consecutive observations. Following the spirit of previous work, this research explores which action or pattern relates to which characteristic of insights. We plan to link interaction and insight by user intent. For instance, with the intent of taking an in-depth look at the issue, the user may retrieve the details of the data for exploration, and then the insight the user gains may be deeply related to this issue. Then the interaction of retrieving details is related to the depth of the generated insight based on a distinct user intent. We evaluate insight from multiple perspectives by directed versus unexpected, correctness, breadth versus depth, and domain value. Regarding user interaction, Grunde and Dou categorized interactions in 4 levels of granularity. There are tasks, subtasks, actions, and events. An action represents a distinct user intent. They are generic across applications, yet semantically rich. So interaction categorization at the action level serves our purpose. We use this prototype to explore our research question. It integrates drug target data from multiple sources. Target here means mutations in different tumor types. Users can select entities from the left list. Once an entity is selected, all its relevant entities are retrieved and shown in the matrix-based view. The columns represent mutations. The upper rows indicate tumor types and the lower rows are drugs. Colored bars in the table cells called drug responses. Mouse over an entity label or its relevant entities will be highlighted. Clicking on a label gathers all relevant entities. Clicking on a table cell, the details and the publication sources of a drug-target relation are shown on the right side. To explore an entity, users can hover over an entity and select it from the drop-down menu. Similar to select actions, or its relevant entities will be shown in the view. Users can compose a note to record their discovery. Entity labels in bold indicates it is mentioning some notes. Users can choose to view relevant notes on the right side. Each note has a provenance view attached showing the interaction steps leading to the notes. We then did a user study with 14 domain experts. Their task is to first input the task they want to explore and freely explore the data and write notes. If they switch to a new task, they need to open the task window and input the new task and continue exploration. Each note must include at least one entity name, like a drug, tumor type, or mutation. As shown in the demo, the tool supports 5 types of interactions. We collected 37 trails that lead to 59 nodes. Some trails are short with one node in each trail. Some are longer and contain multiple nodes in one trail. We manually extracted interaction patterns from interaction trails and named the patterns by the inferred user intent. 2 marked patterns have been discovered in previous work from which we borrowed their name. As mentioned earlier, we categorized the insight from the 4 aspects. 2 raters graded the nodes from the 4 aspects independently on a scale of 1 to 5. If the gradings are correlated, they discuss the gradings that differ by 2 or more points. Otherwise, they go back to adjust the grading criteria and grade again. The final gradings are the average between the 2 raters. As you can see, most nodes are directed rather than unexpected. All nodes are correct, and participants tend to have deep nodes rather than broad ones. The domain values are relatively evenly distributed along the scale. Then we evaluated the correlations between interactions and insights. Results show that, for instance, exploration actions tend to lead to unexpected insights. The drill-down pattern relates to the domain value of insights. We also did a qualitative analysis. We selected 2 groups of participants with high and low domain values of insights and evaluated the domain knowledge involved in writing the insight and insight categories. As you can see from the figure, each group has 3 participants separated by black vertical lines. Blue color encodes the amount of domain knowledge involved in the insight, and the red color encodes the breadth versus depth of the insight. The darker the node is, the deeper the insight is. Comparing the 2 figures, the finding is that one can generate insights with high domain values when using domain knowledge to guide the visual data exploration. Implications of the study are, first, visualization tools can characterize user insight automatically based on user interactions. Tools can also provide personalized insight recommendation. For instance, if a user is elaborating on some entities, the tool can recommend in-depth insights relating to these entities, as the user is potentially looking for this type of insight inferred from the interaction. Thank you for your attention.
Thank you very much, Chen, for this very nice presentation. So now we can initiate our Q&A section for you. Let's see if we have anything on Discord. No, I don't see anything for now. I see people typing though, so I will go with my question then. So, when I was listening to your talk, I was thinking about this concept called slow interaction, I think introduced somehow from Christopher Collins. So Christopher was saying that some users might perform a slow type of interaction. that takes some mental effort to get a deep understanding of the data, which is, of course, this is a meaningful type of interaction, even though they pause when they're doing it. So could this type of user behavior become confusing for your approach, or is there a way we can possibly capture this type of behavior?
Yeah, that's a very good question. I didn't think about, because when I encode the interactions, I didn't consider the time, like interval between the interactions. I just consider the sequence of the actions. So maybe if I consider the interval, there can be different patterns discovered from the interaction. Thank you for the question.
Nice, very, very interesting. So unfortunately, we don't have more time for questions, but I think things coming out, you can go to the chat and engage with the rest of the audience. And that will be the end of our Q&A for Chen.
Thank you.
Our fifth presentation for today, and our next presenter, Benjamin Karl from the Federal Criminal Police Office in Germany, would like to challenge us a little bit our exclusive focus on quantitative factors when assessing the value of visualization, and he will tell us how qualitative factors might also be essential during visual analysis. So, Benjamin, it's all you.
Well, hello everyone, welcome to my VIS 2020 talk. My name is Benjamin Karl, and I would like to tell you something about insight beyond numbers, which is basically the effect that qualitative considerations can have on the result of a visual analytics application. Well, as you know, most of us use the term insight pretty frequently to describe what is the outcome of applying our visualizations and what kind of results can be obtained in visual analytics using one of our applications. However, what I would like to point out is that sometimes the quantitative approach, which is currently predominant in data analytics and therefore also in visual analytics, is not enough to describe every kind of insight that might be obtained from a visualization. I would like to show an example in a few minutes, but first I would like to go a little bit deeper into what kinds of insight we can actually obtain from visualization. So in the literature you will find a number of user studies that tells you that there are essentially three categories of insight we can obtain from visualization. The first one is insight into the visualization itself. This is the kind of insight you obtain from your visual literacy and from studying the legends and the scales that are provided along with the visualization, and it basically tells you how to read the visualization. The next kind is insight into the data. This category of insight tells you something about the data and is obtained by reading of the values, so you apply your knowledge how to read the visualization to learn something about the data. To this end, you have to align your readings about the data, for example, the height of a bar chart, to what you know about the visualization, for example, the scale that is aligned with the side. And this alignment operation causes a higher cognitive load than just reading off values, and therefore is harder to perform than obtaining insight into the visualization. And the third category also requires you to align this knowledge to knowledge that is not part of the visualization, mainly domain knowledge which is present in the user's mind, which is present in textbooks or whatever, but is not part of the data and is not part of the visualization. This kind of insight into the domain is what actually allows you to draw conclusions about the domain from what you have learned about the data before. However, since it involves knowledge that is not part of the visualization, or it's usually not part of the visualization, but is definitely not part of the data, this is the hardest kind of insight to obtain. So most visualizations, basically by the quantitative approach, which is predominant today, are stuck with insight into the data, basically because they do not show additional knowledge that is not part of the domain of the data, but is important for the domain. Let me show you an example in this regard. Here you see a bar chart. Let's first obtain some insight about this visualization. So it's a bar chart that has a scale ranging from 0 to about 7,000 and has months on the x-axis. So basically it's a bar chart telling us that there are some numbers that evolve from around March to around June in some year. And there's a global trend saying that this data, that the numbers first climbed and then they went down again. However, as you also see, there's some kind of pattern here, which is a more local pattern. So we have those local ups and downs. And the question is, what does this tell us about the data? We can already learn something about the data. So we already observed two patterns. And this local pattern says that the data is in intervals, rising and then falling again. Okay, so the main question to obtain insight into the domain would be, what is this visualization? What is this bar chart actually about? So I tell you that these are the positive COVID-19 tests per day in Germany from March to June 2020, according to the Robert Koch Institute, which is the German federal government agency for disease control. So the question now is this pattern, which is shown in purple here, is this pattern actually relevant for the domain? It basically implies that there's a number of small waves when people get infected, and then there are days when less people get infected again. And the question is, where does this come from? Is this important for the domain, or is this probably just some artifact in the data? And the answer is actually it's none of both. So it's not important for the domain and it's not a data artifact. Let me explain why. The red arrows I just blended in show you where the weekends are. So what you see here is that the decline is always during the weekends. Also, there's a bunch of holidays in Germany in May, so there's a larger decrease visible in May on the weekends and especially on continuing holidays. So the point here is that basically domain knowledge tells us that the real reason why there is this decline in the numbers is that many of the laboratories that are making the tests, so the laboratories are not working on the weekend, they are closed. So basically less tests are performed during the weekends than on weekdays. So essentially by this knowledge we see that the decline we see in the intervals is not important for the domain, and this also cannot be read from the data because it is not included in the data when the laboratories are actually open and when they process the results. So basically we can only find out that this pattern is not important and not relevant for the domain from including outside knowledge. And what we know from this outside knowledge is that only this global pattern that we had a rise in March and then it fell down until the end of June is relevant for the domain. So what does this tell us? Well, basically this tells us that the quantitative approach, again I want to pronounce that it is not in the data that the weekends, that the laboratories are closed at the weekends. So basically we see that not all observations, not all findings we can make in the data are automatically relevant for the domain. In this case it was not even a valid observation. The point here is that we need to see this, that to see whether an observation is relevant or even valid for the domain, we need to include additional levels of context. We cannot rely on the data because this information is not part of the data. And therefore we say that we need an additional perspective that broadens our scope of discussion and extends this from the quantitative level, which is predominant today, mainly focusing on the data and quantitative operations, automatic analysis and such. And we need to extend this to include those additional levels of context. And what we call this is qualitative visual analysis, which is basically asking you to point out how exactly insights are meant to be obtained during visual analytics. And we invite you to follow us and to apply these qualitative visual analysis, which we mean is to incorporate in your papers more discussions on how exactly the insights are meant to be obtained. What kind of domain knowledge is necessary to understand your visualization? How exactly are the users proposed to obtain insights? What are the reasoning strategies applied? And it really starts with some it really starts low level with discussing proper scaling according to the domain. It discusses with discussion of the influence of units, and then it goes on until you really discuss reasoning strategies applied. As I said in our paper, we have about 13 examples where qualitative considerations can enhance the presentation, can enhance the results that you obtain by the currently predominant purely quantitative approach. So I really invite you to embrace the qualitative factors contributing to the visualization result and to discuss them explicitly in your papers. So what's in for you? Well, for visualization researchers, the point is that discussing and understanding how insight actually emerged from visualization, we may be able in the future to obtain a better understanding of what we actually do in terms of what kinds of interactions, for example, can we provide that really support our users in better gaining insights and gaining in evaluating their insights against the domain. And for application scientists, they might be able with this additional knowledge to get a closer connection between the visualization and the domain by incorporating the right domain knowledge at the right time to optimally support their users. So with this, I'd like to close my presentation here, and I would really like to invite you to get in touch with us and to discuss terms more via email or via any other means of communication. Feel free to get in touch with us and discuss insight beyond numbers. Thank you.
So thank you very much, Benjamin, for this really interesting call for us to address the sort of domain challenges. There are a lot of questions for you. I'll start with the first, and let's see how this goes. So Danielle is asking something very important, I think. Are there specific types of qualitative analysis techniques that might support applying these ideas particularly well in practice?
So thank you for this question. It's actually in the direction we are doing our further research in this direction. We haven't explored these for the paper at hand. So for the paper at hand, we try to analyze the state of the art and see what the limitations are. However, we are trying to figure out maybe grounded theory as an approach to describe things from a theoretical perspective, and we're also studying semantic approaches. I think I linked a paper to that further up in the Discord chat, studying semantic approaches, how users understand what they see and how they interpret what they see.
Very nice. I think if we are quick, we can have time for one more question. I will challenge it. So Held is asking, do you propose to research tools which enable domain experts to exclude such local irrelevant patterns to provide a sharper view on the subject under analysis? Do you propose that?
Exactly. So this is one thing we propose. So in the center, we propose that we at least should discuss more like what we think brings our users to the conclusions they make. And we exactly propose to develop tools in the long run that should help visualization analysts and visualization designers in the design of efficient visualization tools. So we actually propose in the paper an analysis workflow that should be able to at least drive the discussion in this direction.
Very important.
And we apply this to some examples.
Excellent. Thank you. Thank you very much, Benjamin. And that will be the end of our Q&A session for you. Now we are going to our last presentation for today. It will be from Hullman from Hong Kong University. And now what we will talk about, Hullman will tell us how visualizations can help us analyze the evolution of emotion from large videos. So let's welcome Hullman.
Hello everyone, welcome to my presentation. I'm Hullman from Hong Kong University of Science and Technology. The paper I'm going to present is Emotion Cues, emotion-oriented visual summarization of classroom videos. Emotion play a critical role in understanding classroom learning context. Exploring the emotions of students can help both teachers and parents know about students' learning status. However, it's not easier for teachers to quickly capture and explore students' emotion, especially when they need to pay attention to many students at the same time. Video typing provides great opportunities to tackle this issue. It's very time-consuming to digest classroom videos. General summarization techniques usually extract key frames from a video based on different criteria and do not explore emotion evolution in videos. In addition, it's hard for users to explore students' emotion without providing a user-friendly interface and smooth interactions. It's a non-trivial task to visually summarize and analyze the emotion evolution of a group of people from lengthy recorded classroom videos. First, it's not easier to visually summarize multiple persons' emotion evolution without much visual clutter and allow users to explore the emotion evolution of an individual at the same time. Second, various factors have to be taken into consideration, such as the emotion distribution across time, the correlation between different emotions, face size, and occlusions. Third, many factors account for the inaccurate results, such as complex face condition and occlusion. This inaccurate result may mislead users. To address these challenges, we propose an interactive visualization system. The system supports the visual analysis of emotion evolution from collective and individual perspectives. The system also integrates the model uncertainty into emotion analysis for classroom videos and provides visual cues for reasoning about the emotion evolution. To design our system, we work closely with 4 end users for more than 6 months. By presenting our prototype system to our end user, we gather their feedback and interactively refine the specific design requirements. Here are the 5 design requirements we identified. These figures show the pipeline of our system, including the data processing phase and the visual exploration phase. Our system contains 3 major views, namely summary view, character view, and video view. The summary view contains 2 parts, the emotion archives on the left and the emotion flow on the right, which provide users with both a static and a dynamic summary of the emotions. In the emotion archives, Each horizontal stacked bar represents one person, and the length of each area inside indicates the occurrence number of the corresponding emotion. This view can provide user with a basic emotion information of all the people and the proportion of each type of emotion they display. The emotion flow comprises 4 major parts. The emotion bank many adopt a flow-based design. Colors indicate different emotions. The white of each band encodes the number of people at that time step. The offline bands show the number of persons who have appeared in the videos but are not identified. The influencing factor bar charts mainly show the aggregation information of phase size and occlusion. The height of the bar indicates the phase size detected, whereas the black shading area of the bar represents the occlusion degree. The navigation timeline at the bottom is connected to the video view and mainly used for navigation. Moreover, we use light to connect emotion archives to the corresponding flows, enabling users to track the emotion evolution of each person. The character view visualizes the emotion status of a selected person with a portrait glyph. We adopt a Tero donate chart in this design. Each annual sector on the outer part represents an emotion. The area of each annual sector indicates the amount of the corresponding emotion. Each annual sector is further divided into multiple small slides. Each slide represents information of the selected person at a particular frame. The slide size encodes the phase size and its opacity encodes the occlusion extent. Low opacity indicates that recognizing an emotion at that time is difficult. We provide the original video for user to explore in the video view. When user posts the video, the corresponding face in each frame are highlighted. In this work, we present 2 use cases and interview with end user and domain expert to show the effectiveness of our system. Here we report the case when a teacher was exploring a kindergarten classroom video. 15 children are sitting on the ground and listening to the story told by a caregiver in the video. Manually reviewing a classroom video is often very time-consuming, so the teacher showed great interest in trying emotion on exploring the classroom videos. The first goal of the teacher was to observe the overall emotion status of all the children and the emotion evolution of each child in the video. She chose to look at the summary view first, and the emotion archives directly show the emotion distribution of children, as shown in the figure. She found that the dominant emotion was neutral, followed by sadness, happiness, and anger. The same distribution was also observed in the emotion flow. She could easily find out some happy moments in the video, where the children was imitating the caregiver's actions. Further, she found an interesting child 13, as his major emotion was anger, which is different from other children. She clicked the name of child 13 to further explore details, as shown in the figure. She found that it was mainly due to the partial occlusion of child 13's face, which is clearly indicated by high percentage of the black shading area of the influencing factor bar chart. This kind of visualization of the potential uncertainty effectively influenced her of the potential inaccurate emotion recognition results. Then the teacher explored the emotion status of the children of her interest and compared the emotion of different children. Initially, she felt confused about the sadness emotion. She sorted the children by sadness and selected top 4 sadness children in the emotion archives. Then she checked the snapshot of their portrait glyph in the character view and the corresponding frames in the video view. These children were indeed recognized as sadness in some frames when they were actually listening to the teacher carefully. In addition, she further compared these 4 children. She observed that both children 9 and 7 have shorter static bars compared with children 12 and 5. Similarly, the portrait of children 12 and 5 was denser than portraits of children 9 and 7. After checking the original video, she easily found that this was because the camera did not capture children 9 and 7 in some moments. As shown in the figure, child 9 was leaving during a period of time and coming back later, while the place where child 7 sit was easily occluded by others. Or the teacher felt that it was interesting and effective to use emotion cues for exploring the emotion status of children and check their evolutions. In the second case, we report a professor exploring two seminal videos. One video is about an academic talk, and the other video is an experience sharing event. 13 students appear in the videos. It was easier to distinguish the difference of two seminal events. For the academic presentation, more gray, blue, and red colors, which indicate students tend to be neutral, sad, and angry. The professor finds that when the student looks serious or confused, the back-end emotion recognition tend to recognize their emotion as sadness or anger. For the experience sharing, the professor quickly finds that more yellow color, the student look happier. This was mainly because the second seminar presenter shared many interesting findings and stories during his overseas intern. The professor further explored the engagement of students in the experience sharing video. It seemed that most students was engaged in this activity since the majority of them have long static bar charts and show more positive emotions. After sorting the emotion by happiness, the professor found that student 4 had most happiness. The major emotion of student 4 was neutral, followed by happiness and sadness. The professor was curious about the sadness emotion. The professor further checked the video view and found that student 4 was sometimes feel confused about the content, which looked like that in terms of facial expression. In other moments, the influencing factor bar chart had higher occlusion value. This was because student 4 put her hand in front of her, which makes some occlusions. Sometimes the goal could even not be detected. The professor also explored another interesting student, student 12, as his static emotion bar was much shorter than others, indicating that he appeared in much fewer frames of the whole video. After checking the detail in the emotion flow view and video view, the professor quickly understood the reason for this. Student 12 seemed distracted, and he always bowed down and looked at his notebook. This led to his face could not be detected. Then we conduct interview with end user and domain experts. End user was satisfied with the visual design of the system. They thought our system can help analyze students' emotion. Domain experts appreciate the idea of summarizing classroom video from an emotion perspective. They gave some suggestions for improvement, such as consider other information. Here are some discussion and limitations. For privacy issue, we need to carefully consider and balance the trade-off between positive use case and abuse of classroom videos. For model performance, currently we adopt widely used methods, which can be easily replaced by other advanced models. For emotion recognition, it will be better to directly recognize emotion used in education. For scalability, it will be interesting to explore other design and adopt semantic sampling methods. For generability, our approach can be easily extended to other scenarios, such as analyzing tension situation in psychological settings. For a summary of this work, first, we propose a visualization system to summarize and analyze emotion data extracted from videos. Second, we integrate the model uncertainty into emotion analysis for classroom videos and provide visual cues for reasoning. Finally, we have conducted evaluation to demonstrate the effectiveness of our system. Thanks for your attention. I would like to take any questions.
Thank you very much, Hypen, for this very interesting work. I see the Q&A now from our crowd here. I see a very similar comment that comes from Mikkel and Alper. So there is, first of all, some concern on whether the measuring expressions, facial expressions, is indicative of attention. For example, is it possible that these expressions some students have these expressions, but they don't necessarily means that they are engaged, or it seems that there are such facial recognition tasks are not universal with respect to gender or race or things like that. And then Alper is saying, is engagement, recall, and synthesis generally a good proxy of emotion? So all these comments are questioning, is it possible that we can really detect so many interesting insights from just a facial expression? So what's your experience based on the studies you did?
Okay, thanks for the good questions. Actually, we can detect many things. For example, in education, we can detect the engagement or whether the student bothered or not. But actually, for that kind of data set is not so available because there's not so many label data for that kind of emotion. Currently, I just use the emotion that happier set and something like that to demonstrate the idea, and we can visualize the emotion in the classroom. So in the future, we can recognize engagement, board, and distract, and then so we can visualize, summarize that kind of information, right, with the same similar pipeline. Yeah, and
then let's say that indeed we can capture very successfully the attention of the students. Then I'm sorry, I don't hear you.
Actually, not exactly can capture the students' the internal status, but the emotion can give some hints for their situation, right? For example, when they're happy, they will show the smile, and when they give some hint for the teacher. And if the teacher feel interesting or feel confused, they can refer to the video to look at the real situation. So the tool is basically provide a tool for the teacher to efficiently explore the classroom videos.
So maybe it's a little bit more appropriate for kids who are very expressive with their emotions. Do you think it could be less easy to detect those things when we have to do with adults who may are not so expressive?
Yeah, but I think better measurement can be explored. Currently, just the idea and the visualization system to help the teacher to summarize the whole video and help them to digest the video efficiently.
Very interesting. Well done, Hybrid. So also to point out the last remark from Micallef, which I think is also important, that in case this technique works really, really well and is really, really sensitive, it might have some ethical concerns of how this new tool could possibly use in other setups, for stalking or repression. So if you did a really good job, we certainly have to discuss then how we should, make sure that this type of impressive technology doesn't misused by people. So I welcome a lot of discussion there on the chat about that.
So actually, we need to carefully consider the privacy issue, and we need to balance the abusive use of the tool. And actually, I think the tool can help the teacher to evaluate their teaching. So when they look at the video, it's very time consuming, but once they look at the overview, the teacher can know which part is interesting for the for the student. Then he can improve that part, or some part is boring, right? Then he can further improve that part. Yeah, I think as the tool for the teacher to improve the teaching.
Exactly, and this is a case where the kids can the teacher can make sure about the data of their students. I mean, there is a safety valve there.
Yeah, so for privacy issue, the video cannot help. Public to other people, maybe the teacher for their teaching.
Okay, so context here is super important. Very, very nice, Hullman. Thank you very much.
Yeah. Okay,
and
thank you.
Was our last talk for today. I saw in the Discord you had a lot of, and YouTube probably, I don't see Discord here. I saw a lot of interesting discussions. I'm really want to jump in to see what you're talking about. And it's really nice right now that we have this virtual setup where we can actually continue talking about those things. So I learned many stuff, new routes to explore. We learn about belief updating, predictive models, to capture insights through interactions, or to consider qualitative factors or emotions. And I think all these points can somehow enrich our palette of how visualization domain can really move a little bit beyond the study of perceptual accuracy. So it was really great. Clap for me. And that's the end of our session.
Given a dimensionality reduction scatterplot, we project its original subspace. Through the orientation and shape of our glyphs, both the global trends and local patterns can be identified. To transform the vectors, we use implicit function theorem. We apply our method to different kinds of data.
We propose data-driven space filling curves. Our new method generates linearizations that better preserve coherency than existing techniques. Our method supports 3D datasets, and even multi-scale data on a quad tree or an octree. Many visualizations benefit from our method, for example, visualization of multivariate particles, and visualization
What do you believe is the correlation between labor union participation and corporate profits of different companies? How would you update your belief after seeing this scatter plot? In this study, we use a new elicitation technique to understand how people update their beliefs about correlations after seeing different visualizations with and without uncertainty depictions.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable x and low variable y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.
In cancer research, it's useful to group patients based on disease spread patterns to the lymph nodes. But once we create a new clustering methodology using spatial data, how do we explain spatial clustering to non-experts? In this multi-year project, we dealt with both a participatory design stage and a broader dissemination stage, and distilled specific lessons for interpreting spatial clusters.
How do user interactions lead to insights? We present a case study with a tool that supports 5 types of interactions for exploring drug-target relations. Through an evaluation, we collected interaction trails, manually extracted interaction patterns, characterized the user insights, and explored the relations between interactions and insights.
In this work, we conducted a design study with clinical researchers to develop a visual analytics application for exploring disease progression pathways. As a result, we developed DP-VIS, which seamlessly integrates hidden Markov models with interactive visualizations. The usage scenario and user experiences demonstrate the usefulness of the application to gain useful insights out of disease progression trajectories in a transparent manner.